Okay, in this video, I'm going to cover section 1.1, graphs of equations. Some of the material in this section will be review for you, but it's a good refresher. So we start off just with some terminology here. Remember that a rectangular coordinate system consists of an x-axis. It's labeled right here and it's in green. That's the horizontal axis, and a y-axis that is here in red, and that is the vertical axis. We can indicate any point in this area with an ordered pair. We always give the x value first and the y value second. So for example, if I had a point, let's say right here, notice that has an x value of -3, so that's the x coordinate, and a y value of +2. There's the y coordinate, and that is our ordered pair. Definition: an x-intercept is where our graph crosses the x-axis. To find the x-intercept, you are going to set y equals 0 and solve for x. The y-intercept, on the other hand, is the point where the graph crosses the y-axis. To find that point, you're going to set x equal to 0 and solve for y. So whichever intercept you're looking for, you're setting the opposite variable to 0. So let's go ahead and practice that here. We're going to find the x and y intercepts first with a graph. Sorry, jumping around a little bit on you there. First with a graph and then with an equation, okay? So on the graph, it should be easy. We just need to look. Here is my x-axis right here. That's my highlighted x-axis. Where does that graph cross the x-axis? Well, it's right here and right there. So we need to write those at ordered pairs. The one on the left has an x value of -2 and a y value of 0 because that's what makes it an x-intercept. The other one has an x value of +2 and a y value of 0. So you can see we have two x-intercepts. On the other hand, y-intercepts are where we cross the y-axis, which I have highlighted here in green. So that would be right here where our curve crosses that green line is right there. And that one has an x value of 0 and then a y value of -4. So that's how we would identify them from a graph. For example, number 2 here, we have an equation. So now we have to use those steps I just mentioned in order to find the x-axis, the x-intercept. That's when we're going to set the y value equal to 0. So for that, y equals 0, and then we're going to need to solve for x. So here, we are going to have to remember how to handle absolute value equations. When we have an absolute value equation, the first thing we need to do is to isolate that absolute value. So I'm going to start by adding 2 to both sides of that equation. I'm also going to reorder it here. I like the absolute value part first. And then when we added the 2 over, it became a +2. Now we have an absolute value equation, and we need to remember that we can't just ignore those absolute value bars. The definition of absolute value, that gives us two cases. Either x plus 3 is +2, or x plus 3 is equal to -2. That's the definition of absolute value. So here I'm going to subtract 3 from both sides. So we get one solution, which is x equals -1. I'm going to do the same thing over here, subtract 3 from each side. We get another solution of x equals -5. Now, you don't want to just stop there. When it asks for x-intercepts, it is asking for an ordered pair. So our first number is -1, 0, and our second number is 5, 0. There are our two x-intercepts. Now, we also need to find for this one the y-intercept, which actually often is easier to find. The y-intercept is where we set x equal to 0. So we're going to do that. We use that same equation, y equals 0 minus 3 minus 2. Don't forget those absolute value bars and applying that definition. So 0 minus 3 is -3. But remember, when we have absolute value bars, that strips away that negative sign. The result of an absolute value is always a positive number. So the absolute value of -3 is +3 minus 2. So y equals 1. Again, we want to take that final step to write that as an ordered pair. So this one had an x value of 0 and a y value of 1. So there is our third intercept. We have 3 intercepts for that equation. Next thing we're going to do in this section is we are going to graph some equations. A little later in the course, we will learn some specific ways to graph different families of equations. Right now, we're just going to kind of look at graphing in general. So we're just going to kind of rely on t-tables and plotting points and some basic information to sketch these graphs. So here's our first example. Complete the t-table and sketch the graph. Right now, this equation is not solved for y and it's not solved for x. We could work with it like this, but honestly, I like it a little better if it is solved for y. So the first thing I'm going to do is subtract 2 from both sides. And when I do that, I then have y equals 2/3 times x minus 2. So I'm going to use this for my calculations. Okay, now I've already been given some x values, so those are the numbers I need to plug in for x, and then I calculate what y is equal to. So for this first one, for x equals -2, that means I take this equation, I have 2/3 times -2 minus 2. You can do this in your head. If you're not comfortable with fractions, grab your calculator. Our scientific calculators should have a fraction button of some sort. Ask your instructor if you need help for that. So there it is, 2/3 times -2 minus 2. Notice the negative and the minus, two different signs. So there's our answer, -10/3. And then the other thing we want to do is write this as an ordered pair. So the x value comes first and the y value comes second. And we can repeat that calculation for -1 and 0 and 1 and 3. This is a nice place to use that table button on your calculator. If you have the multi-view calculator, you will have this table button, and then you can type in an equation. So I could type in 2/3 times x. Here's my x right next to the 4 minus 2. There's my equation that I've been given for this problem. I hit enter, and this time I'm going to leave it. I want it to ask me for x values because I've been given some specific x values I need to use. I've used my table button before, so there's already numbers in here, but I just type right over the top of them. So for x equals, oops, -1, enter. When x is -1, y is -8/3. When x is 0, honestly, we could do that one pretty easily in our head, but I'll just go ahead and enter it here. When x is 0, y is -2. When x is 1, y is -4/3. And when x is 3, y is 0. Okay, so then again, ordered pair. I'm not going to fill every one of these in. I'm going to actually pick these two. So that one is 0, -2, and 3, 0. And then it's going to ask us to graph that equation. So graphing it by hand, we have a whole t-table of points here, but I would like to use these points that are whole numbers. They happen to be our intercepts. So x equals 0, y equals -2 would be right here. And x equals 3, y equals 0 right there. And then we connect those points with a straight line. And there's our graph. Next one, okay, this is an x squared, so that's not going to be a straight line this time, okay? We can still fill in our t-table the same way, but this is going to be a little bit different shape. Again, we'll start with this first x value, and I'm going to plug it in right in here to our equation. So if x is -2, be careful with these signs because there is a negative in our equation, and then we are also plugging in a -2 for x. So the -2 gets squared. This -2 times -2 is +4, but then we still have that negative sign in the front. So it's actually -4 plus 4, which is 0. So our first ordered pair is -2, comma 0. And again, if I want to fill in that equation here, negative x squared plus 4. I can get my points real quick and easy using that table button on the multi-view calculator. -1, that's the next number. Look, let's share some x values. For -1, x is 3. And for 0, x is 4. Oops. And 3's on my list for x equals 3, y is -5. And then I just need to type in a 1. And when x is 1, y is 3. And again, each one of those ordered pairs, just x value comma y value. Okay, so let's plot those points. X equals -2 and y is 0. X equals -1 and y is 3. 4, or sorry, 0, 4. And then 1, 3. And then 3, -5. So we should have at least a little bit of familiarity with that x squared. We're going to talk about that more later in the semester, but that kind of graph is not going to be a straight line. It's going to be a parabola or a U shape. And if you connect these points we have, oops, that's a bad drawing. Let me try again. You can kind of see that it starts to make a downward facing U. So this is a parabola facing downward. Now, when you get into WebAssign, when you do these graphs, listen carefully. You need to do this. The first thing you have to do is select the shape of your graph, okay? So there are a couple buttons down the side of the graph. So if you have a linear equation, that means there's an x variable, but it's not squared. It's just a plain old x, okay? That means we're going to pick this double arrow right here. You have to click on this once, this arrow, this straight line button, and then you'll see these three choices, and then you click again to click the one with the double arrows. That is for a linear equation, okay? For a quadratic equation, I don't know why these are crossed out. They shouldn't be, okay? If your quadratic equation, that means something is squared. If the x is squared, you want the parabola facing up. It could be technically up or down. If the y is squared, you want the parabola facing to the side. Again, you'll click this button once, and then you'll see two choices, and then you click on the appropriate one. Now, if you are asked to plot an individual point, like if you need to plot the point 2, 3, then you will use this point tool. If you are clicking on points that will draw a straight line, do not use this point tool, use the straight line, okay? So straight line, quadratic equation, points only, okay? Again, ask your instructor if you need help with those WebAssign graphs. Okay, next thing we're going to look at in this section, we're going to talk about symmetry. And symmetry is one of those things that's a little hard to describe. You kind of know it when you see it, but we have a couple examples here. X-axis symmetry is the first type of symmetry we're going to see. And that means if you were to fold your paper in half on the x-axis, right there down the middle, just imagine folding it in half, okay? That means anything above that line would match up with anything below that line once you fold it in half. Another way to think about it, if we have a point right here on our graph, that same point, except with the opposite sign on our y value, also has to be on our graph. That's how we get x-axis symmetry. Every point above the x-axis has to have a matched partner below the x-axis. That's x-axis symmetry. Sometimes we have y-axis symmetry, okay? And that means if we folded our paper in half right on the y-axis, the graph, two parts of the graph would meet up, okay? Similarly, if we have a point to the right of the y-axis, that point has to have a partner to the left of the x-axis. That means the 2 points would be the same, except the x values would have opposite signs. That's how we determine x-axis symmetry. And origin symmetry, we can't really think of that folding in half thing. It's a little bit like a fold and a twist. It's kind of symmetry on the diagonal. But the best way to think about it is if we look here at any point on the graph, x and y, if you flip the signs of both of those coordinates, -x and -y, that point also has to be on the graph. So let's look at some examples and see if we can identify what kind of symmetry is going on here. So number 5, I notice if I kind of have an imaginary dashed line right down the middle here, look, when I look to the right of that dashed line and to the left of that dashed line, no matter where I look, I can tell that there are partner points. If there's one to the right, there is the one to the left that is the same distance from that axis, okay? So this one has y-axis symmetry. Okay, my next one, this one, when I look at that, I kind of see a line right here that would cut this graph in half. And that happens to be right there on the x-axis. Okay, so if that cuts our graph in half, one thing I notice is that for every point above that line, there is a matching point the same distance away below that line. Anytime we have these pairs of points, both above and below the x-axis, that's when we have x-axis symmetry. Next one is this number 7, this nice little wiggle graph. We got a little squiggle wiggle going on in the middle. Anytime I see a graph that is sort of focused on the diagonal, two quadrants that are diagonal from each other, I am thinking about origin symmetry, okay? I think this might have origin symmetry. If I want to check that out, what I can do is I can take a look at a couple points on this graph. I'm going to pick this one right here. Let's look at that point. Let's say that it's approximately the point 2, -6, okay? If this graph has origin symmetry, that means the point -2, +6, opposite signs on both, also has to be on this graph. And is it? -2, oh, it was 5, not 6, isn't it? Sorry, 5. Back it up, change that to a 5. I read that number wrong. I'm sorry. Okay, so 2, -5, and -2, +5, those are both on this graph. And it turns out that we could do that for any ordered pair. This point and this point and this point and this point. Every pair has a partner with opposite signs. So this one has origin symmetry. Okay, this last one. One of the things I do when I try to look at these graphs and see if there's symmetries, I kind of try to imagine where the line would be that would sort of cut this graph in half or split it down the middle. If I were to try to split this one down the middle, I maybe would try like here. Does that split it down the middle? Well, this point here does not also have a point above, so that doesn't really do anything for me. What if I tried to kind of split it down the middle this way? The points don't match up there either, and they definitely don't match up on either side of the x-axis or the y-axis. So this one actually has no symmetry. And again, if I wanted to see that, I could pick a point on the graph. I'm going to pick, let's see, how about, I'm trying to pick one that's pretty close to whole numbers. How about this right here? That is the point. Oh no, I want one that's not 0. This one's pretty close to a whole number. Not, no, this is just not easy to look at a graph. Let's see, I should have given something. Here's a good point right here. That is about the point -1, 1, okay? If this graph had x-axis symmetry, okay, that means that this same point with the opposite y value would have to be on our graph. -1, -1. And it's close, but it's not really. You can tell there's actually a little curve away. Again, this graph isn't giving us great detail because of all the fractions. It's a little hard to see. Again, if I pick that reference point and I change the sign of the x value, that would tell me if it had y-axis symmetry, and that point clearly not on the graph. And then if I change the sign of both coordinates, 1, -1 would be right here, also clearly not on the graph, so no symmetry. A lot of times you can tell just by looking at it, okay? But if you need to look at the points, that's kind of how we do it. So far we looked at symmetry by looking at a graph. We can also discuss symmetry by looking at an equation or algebraic tests of symmetry. If your equation is symmetric with respect to the x-axis, When you replace y with negative y and then simplify, you would end up with the exact same equation you started with. Okay, that's x-axis symmetry. If your equation is symmetric with respect to the y-axis, when you put in x, when you replace x with negative x and simplify, you end up with the same equation you started with. And if it was symmetric with respect to the origin, you replace both x with negative x and y with negative y. You end up back where you started, and that's going to give you symmetric with respect to the origin. So let's take a look at how to do that with a few equations, okay? So with each one of these equations, we just have to step through the different types of symmetry. Once we find symmetry, we stop. We don't have to try the others. But for each one of these, we're going to check for x-axis symmetry, y-axis symmetry, and origin. X is when we put in the negative y is when we put in the negative x, and origin is when we put in both as negatives, okay? So let's start with x-axis symmetry. That means I'm going to rewrite this equation, but anytime I get to y, I'm going to put negative y in its place. Okay, so it used to be y squared, now it's negative y squared. And then we want to simplify it if possible. So we got to think about, what is this? Negative y squared. Well, negative y times negative y, what happens when you multiply a negative times a negative is that you end up with a positive. So we can actually simplify this into just minus y squared, because that negative y times negative y, the negatives cancel each other out, and that is just y squared. And notice that this is exactly the equation we started with, even though we plugged in a negative y. So that means we have x-axis symmetry for this equation. Since we found x-axis symmetry, we don't need to test for the other two types. Okay, next one, number 10. Let's again check for x-axis symmetry. That means we're going to put negative y in. And there's not a lot of simplifying we can do here. We can solve for y if we divide both sides by negative 1. If we do that, we would get y equals negative x cubed. That is not what we started with, so this is no for x-axis symmetry. So then we want to look and see, does it have y-axis symmetry? And that's when we put in a negative x. So y equals negative x cubed. And when we squared a negative number, it became positive. But when we cube a negative number, it stays negative, okay? Because negative 1 times negative 1 times negative 1 is still negative 1, okay? So we cannot get rid of that negative sign. What we can do if we wanted to is we can write this as negative x cubed. That is equivalent for odd exponents. The negative stays, whether we have parentheses or not. This is not the same as what we started with, so this one has no y-axis symmetry. So then we have to try the last one, which is origin. So we put in a negative y, and we put in a negative x. Remember that when it's an odd exponent, we don't actually need those parentheses. And then when we get to this point, if we divide both sides by negative 1, what do we end up with? We do end up with positive y equals positive x cubed. That is exactly the same equation we started with. So this one has origin symmetry. Oops, sorry, my screen jumped a little. Okay, this next one, number 11, again, we just have to work our way through. Check for x-axis symmetry, means putting in a negative y. We divide both sides by negative 1. Remember, we have to divide both terms by negative 1. We get y equals negative x cubed minus 4, not what we started with, so no for x-axis. If we're checking for y-axis symmetry, that means we put in a negative for the x. And with an odd exponent, we can remove those negative signs, but this is still not what we started with, so no, it does not have y-axis symmetry. And for origin, we put in a negative for both. We can simplify there. And then we can, again, divide both sides by -1. Remember, we have to divide both terms by -1. So we get negative y divided by -1 is positive y. Negative x cubed divided by -1 is positive x cubed. Positive 4 divided by -1 is -4. So this also is not what we started with. So this one actually has none of the types of symmetry. Some equations don't have any symmetry. The only way we can know that, though, is test all three of them. And then finally, this last one, I'm going to give you a little spoiler alert. We're just going to jump to the right type so we don't have to try all of them. We're just going to jump right in and test for y-axis symmetry. Remember, we do that by plugging in a negative value for the x. And remember that when we have an even exponent, that clears the negative signs. A negative number, when we square it, becomes a positive number. And this is exactly what we started with at the beginning. So this one does have y-axis symmetry. Okay, here's another kind of problem you could see for symmetry. It gives us a little graph here. It says, assume the graph below has symmetry with respect to the y-axis. Complete the graph. So this is really just half of our graph right now. Okay, if we know that it's symmetrical with respect to the y-axis, what that tells me is that any point on my graph, xy, has to have a partner point that has the opposite x value, okay? So if I pick this point right here, that is the point 2, 0. That means -2, 0 also has to be on my graph. If I pick this point right here, that is 1, 3. That means -1, 3 also has to be on my graph. And that, plus what I know about symmetry, gives me a pretty idea of what the other side of that graph has to look like. There we go, we filled it in. Okay, a couple formulas that are in this section 1.1 are our distance and midpoint formulas. The distance is, as it sounds, the distance between 2 points. And here's our formula. The midpoint formula, if you're given 2 points, you can find the point in the middle of those two, and that is this formula. So let's try them both. Example 14 here, we are given 2 points. Remember, it's xy and xy. If you want to label them, we could call this x1 and y1, oops, if that's our first point, and x2 and y2, our second point. That might help us with our formulas. First, it says find the midpoint. Make sure you're using the right formula. Midpoint is this one. So midpoint says x1 plus x2. So x1 for us is -3. x2 is 5. Divide by 2. That's going to be our x coordinate of our midpoint. And then y1, which for us is 7, plus y2, which is 1, divided by 2. That's going to be the y coordinate of our midpoint. So now we just have to do some simplifying. -3 plus 5 is 2. And 7 plus 1 is 8. 2 over 2 is 1. And 8 over 2 is 4. There is the midpoint. That is the point that would be in the middle of the 2 points we were given. Just important to note, just something to remember. A midpoint is always an ordered pair because it is a point. Okay, now we want to take those same 2 points, but instead we want to find how far it is between the 2 points. So we're going to apply this distance formula. The square root of x2, which for us is 5, minus x1, -3, and that is squared. And then we're going to add to that y2, which is 1, minus y1, 7, and that is squared. And then you can rely on your calculator. You can do some of this by hand, whatever you're most comfortable with. I'm going to simplify what's in the parentheses first. So 5 minus a -3 is 8 squared. And 1 minus 7 is -6 squared. 8 squared is 64. -6 squared is 36. Remember, negative times negative leaves a positive. That is the square root of 100. Beautiful. That is a perfect square. So the square root of 100 is 10. 10 is the distance between the 2 points we were given. Now there's another kind of problem in this section that we can use the distance formula for, and that's one like number 15. 15 says find all the points on the x-axis that are a distance of 5 from the point -2, 4. And this is the kind of problem that I think it's helpful to have a little sketch to see exactly what they're asking us to do here. Okay, so here's our little coordinate system, and they're asking us about this point, -2, 4. So let's plot that. And it can just be a rough sketch. It doesn't have to be perfect. Okay, so there's our point, -2, 4. Now we're going to start with this first. What if it said find all the points that are a distance of 5 from -2, 4? Okay, if it said that, that means we'd go, let's see here, 1, 2, 3, 4, 5 units in that direction. 1, 2, 3, 4, 5 units in that direction. 2, 3, 4, 5 there. Okay, these are all 5 units away. And if I did that in every direction possible, what would I get? I'd get a circle, right? These points on this circle, pretend like it's a nice circle instead of a wobbly circle. But these points are all 5 units away from that point in the middle that we're interested in. But our problem doesn't ask us to find all the points that are 5 units away. It asks for all the points 5 units away that are on the x-axis. So they are asking me to find this point right here. That's on the x-axis and on my 5-unit circle. And they're asking me to find this point right here, which is also on the x-axis and also part of my circle. My picture is wobbly and not to scale, but this gives you the idea. So we are looking to find these 2 points. Each of them is 5 units away from that point we were given. So we're going to apply the distance formula. You guys have it just above, but I'll copy it down here just so we have it right in front of our faces. Okay, so the distance is 5. So we're going to replace that d with the number 5. And then, well, we have a point right here, right? I'm gonna use that. I think that's easier if we call that point 2. So that's x2 and y2. But what's the other point we're gonna use? Well, it's gonna be this one, okay? And we don't know the x value of that point. We're gonna call it x1, okay? We don't know what that is, but we do know the y value of this point. Any point that is on the x-axis has a y value of 0. And because that point is filled in, we can now solve for x when we write out our equation. So let's fill in the numbers. x2, that's the point we know, minus x1, that's the point we don't know. Okay, that's the x value we're trying to find, plus y2 is 4, minus y1, which is 0, squared. Now we have an equation with only one variable in it, so we can solve that for x. So first thing I want to do is simplify inside what I can. I'm going to leave this alone, this part alone for a minute, but this, I can simplify that. 4 minus 0 is 4, and I square it, that is 16. Okay, and then the next thing I want to do is, I don't like that radical. I want to get rid of it. When I'm solving equations, to clear a radical, I need to square both sides of that equation. So 5 squared is 25, and now the radical's gone. Okay, I'm trying to get at that x. So next thing I see is, how about we move that 16 over? 25 minus 16 is 9. And again, trying to solve for that x. It would be nice if that exponent was gone, right? So I need to take the square root of both sides. And when we are solving equations and we take the square root of both sides, even root of both sides, we need to remember to put in a plus or minus, okay? Square root of 9 is 3. And over here on the right-hand side, the radical and the exponent cancel each other out. So I'm left with this. So I now have two equations. -3 equals -2 minus x. Or +3, because remember it was plus or minus, equals -2 minus x. So in both cases, I'm going to add 2 to both sides. I get -1 equals negative x, or 5 equals negative x. Divide both sides by -1, and I get x equals +1, or x equals -5. Oh, I circled them, but I shouldn't. Those aren't quite my final answer. Read the directions. My directions said find the points on the x-axis. So I need to write them as points. The first one on the x-axis is 1, 0. And the second one on the x-axis is -5, 0. And if you go back and look at our graph, you can see, again, my circle wasn't perfect, so this one doesn't look quite like 1, 0, but that's what we found here. And over here is the -5, 0. So there's our 2 points. Okay, we're going to do another one. And this is our last one for this section. And when we scroll to this one, number 16, it looks almost like exactly the same problem. Find all the points on the y-axis that are a distance of 5 from the point -2, +4. The only thing that changed in this whole problem is that letter right there. In our last example, we found the points on the x-axis. This time, we're going to find the points on the y-axis. So setup is the same. I'm still going to show you that circle, right? There's our point. And we already talked about how all the points that are 5 units away from there, see if I can draw it a little better circle this time. All the points that are 5 units away are on this circle. I don't know if that's better or not. Last time I was looking for this one and this one, right? Because they were on the x-axis. This time I am looking for this point and this point because we want the points that are 5 units away and on the y-axis. Okay, so we're looking for 2 different points. So when we set up our equation this time, our distance is still 5. I did it the opposite way I wanted to last time. I actually want to call this is going to be 0.2 down here, and this is going to be 0.1. So this is x1 and y1. And down here, I'm going to have x2 and y2. So this time, my point is on the y-axis. So my x value is 0, and my y value is my one I have to solve for. Okay? So if we do x2, 0, minus x1 squared, plus y2 minus y1 squared, and then solve. Almost everything is the same. It's just this point, the unknown point, that changes. When it was on the x-axis, it was x0. When it's on the y-axis, it's 0y. But we're going to solve this in just the same way we did last time. First, simplifying, 0 minus a -2 is +2, and we square it, and we get 4. And then I'm going to square both sides to get rid of that radical symbol. And I'm going to subtract 4 from both sides. Now I want to get rid of that exponent, so I'm going to take the square root of both sides. Remembering when I rewrite, if I take the square root of both sides, I have to include a plus or minus. Last time we had a nice little perfect square there. Square root of 21 doesn't simplify, so we just leave it as a radical. And then we need to add that 4 to both sides. And there it is. There's our 2 numbers. Y equals 4 plus or minus the square root of 21. Okay. If we were to write that as ordered pairs, it's 0 and 4 plus the square root of 21. There's one of our points. And 0, 4 minus the square root of 21. So again, we found these 2 points, 2 answers, 2 points. And there it is. And that is section 1.1.